emission scenarios in AR5, if there is an AR5. And until, I think, a few months ago, I would have been able to give that talk. Now I'm no longer sure really what's happening, but I'm happy that other colleagues who have been involved in these discussions, like Richard, are here, so maybe they can fill in. But what I decided to do is, since there is a little bit more time than I originally thought, I will talk a little bit about the history of scenarios in the IPCC, emission scenarios, our current work on AR4, and what are the major findings, and then about what might be the ways forward for the AR5. So that's basically the plan. I wanted to start with perhaps something very general, and I apologize for perhaps starting with really little bit trivial position, but I just wanted to refresh your mind that scenarios, the way we use them to look into the future developments of emissions or energy on land use, they are really tools to deal with uncertainty. In some ways, you can say that they are descriptions of plausible futures. They should be always plausible from my point of view. They should make lots of sense and have some kind of internal logic. In more narrative literature, scenarios are considered to be visions of alternative futures. In our context here, we look at the various driving forces that will influence the future emissions, like population, like affluence, like technology, and then look how they interact with each other and what emissions outcomes result from that. There is another element that I think is quite important, at least now in the AR4, is what is the relationship between the long-term and the short-term scenarios. Because many of the decisions that are being made today, for better or for worse, are made with a very short time horizon. And yet, I think this community knows that's the best than everybody else. The long-term commitments of those decisions are there. And so I think that there is a role of scenarios trying to link those two time horizons. Another thing I wanted to say is that scenarios are always context specific, so it's important that in this context we are talking about emission scenarios. One would probably use different methodology and different tools if the scenarios would deal with the evolution, let's say, of aviation or mobility rather than of carbon dioxide, greenhouse gas emissions, and so on. And so that as a consequence of that is how the scenarios are developed depend very much on whom they're trying to inform or what they use it will be. And I think that has been quite a lots of extensive discussion in IPCC ever since the beginning. What is the role of scenarios? What types of scenarios one should have? So I think that predetermined quite a lot of the history of the scenarios in the IPCC. And here is a kind of a chronology from the beginning. The first set of scenarios was already developed for the first assessment report, so-called SA90 scenarios. And I would characterize those as primarily input to drive the climate models. They had socioeconomics there and human dimensions, but relatively in a rough form. The next set, already 2 years later, and that's perhaps the most famous set, was that IS92 scenarios. There were 6 of them, but usually one was used in most of the analysis afterwards, the central case, the so-called IS92A. Then in 95, IPCC decided to evaluate the role of scenarios across the various working groups and what would be the characteristics and so on. And based on the outcome of that special report, panel made the decision to develop yet another set of scenarios in 96. And that resulted in the SRES set. Those are the scenarios that you talked about yesterday, A1, B2, very creative names. And for political reasons, I guess. So that was the set that was produced here in year 2000. That set of scenarios were pure reference scenarios, defined by IPCC in the terms of reference as scenarios that should not have any explicit climate policies in it, and certainly no new climate policies. Going back to 2000, that means also no Kyoto Protocol, for example. At that time, it was not ratified. In 2001, in the TAR report, Working Group 3 used these SRES scenarios to produce a set of stabilization scenarios, or rather, modeling teams produced a set of stabilization scenarios, but these were CO2 only. And that's important to keep in mind. So now in AR4, the focus in the Working Group 3 on the scenarios, these long-term scenarios, is primarily on stabilization, but in the multi-gas context. All of the greenhouse gases and the other active substances. So that's basically the history so far. And here is the hypothetical. I think yesterday one of you showed 2013 as a possible date if there is an AR5. The number that in the task force group on the new scenarios was used was 2014, but it doesn't matter because decision has not been made. But I think working backwards, if there is an AR5 and if a new set of scenarios would need to be developed, there is almost not enough time to do it. If you considered, for example, that SRES took almost 4 years, even if we do it faster today, it would still mean 3 years. Probably won't start in 2007, so they will be not ready before the end of the decade. And that has been, I think, one of the vexing problems in thinking how the best to do the scenarios, because it would take a long time to develop the new set. Here, I want to show you some of the characteristics of scenarios. I'm not sure you're interested in all of that, but I think the climate modeling community always has argued we need only very, very few cases. If you give us lots of cases, it's too difficult and not possible to do. And that this gives you maybe a little bit of illustration how we, who work on the emission side, have exactly the opposite problem. Our tendency is to produce a large number, ensembles of scenarios, and then the challenge is to pick just very few that would be reasonable then for the climate modeling community to look into what the consequences are. And so it all actually started okay in the old days. In 1990, there were only 4 scenarios, and in fact, there were just 2 genuine scenarios and 2 stabilization cases. So there were 2 reference scenarios and 2 policy cases in the old set. The IS-92 had only reference scenarios, even though the lowest scenario was consistent with stabilization at 450. That's what I recall now. It's probably not exactly correct, but it didn't have any explicit climate policies in it. These are some of the other characteristics. If you're interested here, there was only 1 population projection. In IS-92, people already felt that the uncertainty on population is very large, and since it's such an important driving force of what will happen to humanity over the next century, they looked at the 3 alternatives, high, median, and low. They had already 6 different economic development paths. In this old case, there were really only 1 or 2, depending how you look at it. And IS-92 was significant, I think, in general, because it was right at the forefront of literature in that time to include all of the greenhouse gases, including also sulfur, NOx, and SOx. And so it was quite a comprehensive treatment of emissions. In the SRES scenarios, one of the requirements was the different models be used to develop the scenarios. And the team decided to have 4 different future visions, if you wish, 4 different development paths of population, economy, and so on. And so if you just do the arithmetics, 4 times 6, you already have quite lots of scenarios. And given that people did variations, we ended up with 40 scenarios that were divided into 4 so-called families. That means they shared some of the basic assumptions that allowed to understand a little bit better the differences in the scenarios that are due to different modeling approaches, because we have completely different paradigms how to model this, and the difference that's due to the initial assumptions. But I think what's important for the climate modeling community, we, at the end, IPCC rather chose 6 of those 40 that were considered to be illustrative, and that would be the set that would represent the whole portfolio of possibilities. So it ended up with the same number of scenarios as before. When you do mitigation based on this 4 different futures, and you do a couple of stabilization levels, in this case there were 4, and there were 9 models already by that time, and that even blows up further. So all of a sudden, IPCC ended up with 80 mitigation scenarios. So, and then again, few cases had to be picked that would be representative of the set. In the current assessment, IPCC is not attempting to induce and has not asked the community to produce the new model, the new scenarios. That's important to say. The current assessment, AR4, is a more traditional assessment where IPCC looks at the literature and just looks what's out there in the literature. At the same time, that's a real problem because very often it's difficult to understand why a particular scenario looks the way it looks. It's difficult to know what's behind it always in detail, but the assessment is based on the peer-reviewed literature. And this is a very large number. Just to give you an impression, there are about, the last count I'm aware of, about 700 emission scenarios in the literature altogether. So these are these spaghetti curves. I'll show you some of them. And since the production of the last set that has been used, the SRES scenarios, there have been another 200 scenarios added to the literature. So what we tried to do, and there was an intensive discussion between some of the climate modelers and the scenario people during the last year, whether it's possible from the new literature to pick up a representative set. And we actually think we have managed to do that. We have picked from 6 different models, a number of baseline scenarios and a number of multi-gas stabilization that we, at that time at least, recommended would be a representative set. If one would model those, then one would have the uncertainties both on the stabilization and the reference scenarios.
Who was the we?
It was a subgroup of the scenario that's assessing the scenario, the literature on the emission scenarios, in particular modeling teams that volunteered to do the work. There were 6 modeling teams, including Steve and his colleagues. And the stabilization levels that we chose, and this is new, maybe I should say that, one was 5 watts per square meter, roughly, because not all models get it exactly there. Another one was 4.5, and this might be significant, roughly 3 watts per square meter. That corresponds to the heroic European idea of stabilizing at 2 degrees. And so there is a new literature. This is really something that's happening new in the emissions literature. There's a growing number of scenarios that tries to deal with that, usually with an overshoot, depending on what the baseline is.
How many were, this was what we were trying to negotiate between work groups 1 and 3,
That's right, yeah. Okay, well, here is a more complete list. So you can see here which modeling teams participated. These are the scenarios that were produced by different models. And each of them did a baseline, and these are the various stabilization levels that they produced. As you can see, we have a largest bunch in 4.5 watts. That's probably the most interesting interval, and there one would have the diversity between the models, and then few runs in the relatively low stabilization levels of about less than 3 and a little bit more than 3 watts per square meter. And these are all multi-gas scenarios.
So how different are the emissions between all those models at 4.5?
The emission paths are very different. I can find the graphic and show you. I don't have it in this talk. They're fundamentally different, especially when you come to this area, because, I mean, just think of the following. If you take, I don't know how familiar you are with the SRES scenarios. For example, B1 scenario that describes sustainable development in the future, stabilizes, it's consistent with stabilizing roughly at 550 ppm, roughly speaking. Now, if you take that as a reference and want to go down to 450, that's clearly much easier than if you're taking a reference where you have 1000 ppm. And so this is a large variation across the models depending what baseline they used, and it gives a diversity of emission paths.
So the reference scenarios are all really different.
Some are similar because they're based on SRES, updated versions of SRES. Others are really modeler's choice. So, for example, the MIT reference was a modeler's choice reference.
Do they correspond to any of the other SRES scenarios?
Like they cover the range. This is what's interesting. I mean, that's how we chose the set. They cover the range. They cover the range of modeling approaches. They cover the range of emissions. And we thought at that time it also covers the reasonable range of stabilization.
So just as an aside,
yeah.
and people probably weren't aware of this, we were trying to negotiate this between work groups 1 and 3, and we were trying to work out a way that we could include some of these new scenarios in work group 1 in chapter 10. And it got to the end, and we just couldn't pull it off. It just was too new. A lot of them were not yet published, and so we encouraged Work Group 3 to actually show some climate-related results. And I was curious what you decided to do about that.
Well, I can show you the chapter. With a simple model, we tried to relate some of these trajectories to the delta t's
Okay.
divided
So
in the classes.
You did decide to include some
Yeah,
climate.
yeah,
that's
but
good.
I think this is also up to the review of the working group one.
Right.
So I would encourage people to look at chapter 3 now that it's out to review and provide us feedback. I think it's one possible way of interacting on this topic,
Yeah.
since it was not possible in AR4, perhaps post AR4.
Right.
Naki,
Yeah.
I know that the image model has gridded land use
Yeah.
information that goes along
Yes.
with those. Do any of the other scenarios have that? Or?
Well, our new version has associated with it also gridded. In fact, with some of our scenarios, we also have gridded population and GDP. Yeah, I don't know, Steve, in your case?
Yeah, the model itself doesn't operate on gridded basis, but we have gridded input data we use for it, so it can be produced.
Yeah.
I'm just thinking as you start to run these Earth system models forward, in some AR we're going to need the gridded land surface changes
Well,
to go along with the emissions.
But there's actually, there's also methods that people have used to take where aggregate land use changes and transform them to gridded changes, based on similarity and characteristics and so on. Proximity, characteristics. So that can be done. But the question actually you need, not all these models actually have land use
No.
that changes. So, that's actually the more fundamental one.
Well, that was always the problem, and one way of dealing with that is when people have some of the harmonized assumptions that go into the models, then you borrow land use from another model, and that way at least you have a diversity, let's say, on the energy side. But that's an inherent problem that's going to continue. And another related issue is that for example, what Steve did for stress scenarios with other colleagues was also to grid some of the emissions that need to be spatially specific.
Is mitigation achieved in the same way?
No. No, you mean from the point of view of burden sharing? Each modeling team has its own scheme.
The technology, some will go for carbon storage, other for...
Yeah, well, we can discuss that later. In principle, the portfolio of technologies is equivalent across the models. They share similar ideas. You have carbon capture and storage. You have nuclear. You have biomass for fuels, for liquids, for electricity. But what really varies across the models is what are the assumptions about the technology. So the portfolio is very diversified. If you look into the models, you will see fundamentally different structure, for example, of the energy system and technologies that are behind it.
So the share in different technologies will be very different.
Would be different across the models, yeah. That reflects the uncertainty, I think, and the state of the art. Now I want to go a little bit to the substance and wanted to just give you some intuitive feeling of how these numbers look like that we are dealing with. And since we, because of the nature of the problem, have to look 100 years into the future, that's really stretching the imagination of what the models can do. I think it is useful also to put the last 200 years as a reference so that one has the dynamics.
Do these start in like 2005 now?
Models starting usually 2000 is the base
So
year.
there's
SRES was 1990 was
Right.
the base year.
So you're using 2000 for all these.
The base year issue is another huge problem. So better that we don't enter that debate now.
So you don't try to look at the 20th century. You don't do any of that analysis.
Well, some modeling teams have done backcasting, but that's not part of this analysis of scenario comparisons. We start in the same base year and look forward.
It's actually rather difficult to do given
Yeah.
the structure of these models.
Yeah.
It's a lot of it's very somewhat context dependent. It's not, they're structured different in the Earth system model where in principle the year just doesn't matter. You just put in different inputs. And in some way, maybe we'll someday get to a point where that's more the case, but it's certainly not now. So.
Yeah, just if you have an impression. For example, in our model, when we calibrate the base year, we also have to calibrate the capital stock because model has to make a decision. So some history goes into it. But we don't start running the model in 1900 because we would have to force it to emulate what happened then. So what's the point? So basically, the history would be a base year. But these are the historical data, just that you have an impression of what our perception is of the future across all of these various scenarios vis-a-vis the history. Population now is officially 6.5 billion in the world. And the current thinking is somewhere between 6 and 7 by the end of the century as one of the high likelihood outcomes, curving to a maximum of about 8 to 9 billion by the middle of the century. But one cannot exclude the possibility of having 2.5 to perhaps even 3 times the current population. So even here, future is open despite lots of inertia. Economic growth, you can see economy grew about factor of 18 during the last century. When one looks forward, there are very, very few scenarios that anticipate similar growth rates in the future. Most of the scenarios will be in the range of 5 times to 10 times the current economic output over the 100 years. So you can think that most of these trends are S-shaped. We are now in the middle of the exponential growth, and as you look in the scenarios, despite big variation, the growth left to be accomplished during the next century is significantly smaller. Energy is the same, yeah?
What's the fundamental reason for that? I'm not an economist, so why is it so hard to get another?
Well, I mean, I think there are many reasons. I mean, starting from resource constraints, starting with issues of development, that, you know, there are many, many poor regions in the world. I mean, there are thousands of reasons. I mean, I have worked with my colleagues very hard, and that has been occasionally also criticized, to think of exceedingly affluent worlds. And these are some of these scenarios here on factor 18. And one problem you have in that kind of scenarios, at least from my perspective, is, for example, to make Africa develop, to have the conditions where the actually development takes off. And so none of these scenarios, no matter how high the growth is, actually achieve in the developing countries that what we have here. There is only some relative narrowing of the gap, but in absolute terms, the gap either grows or stays at least the same.
It's resource limitation or something that's the ultimate thing.
It's resource limitation. It's
Not resource. I mean, not in the sense of you run out of resources.
No, you don't run out of oil, for
Not
example.
in the simplistic sense. It's
No.
more human capital resources, for example, dynamic resources, education. I mean, there's a lot of other issues. It's more in a more broader sense.
Well, also accumulation of capital, investment decisions. So there are many factors that go into in the models.
And what's probably more important is the energy line. The
Yeah.
fact that we're not going to go another.
And the energy line is, from the point of view of emissions, as Steve says, it's critical. You see, during the last century, we had a factor 10 growth in the energy consumption. It's unbelievable how huge the expansion was of energy use, leading to this large increase in carbon dioxide emissions. But in the future, in the more sustainable scenarios, even baselines, energy might increase only marginally. That's energy input, not the services that energy provided. That grows in any case. But in a more fossil intensive scenarios, one might have up to a 6-fold growth. So that is that upper boundary that I think some of the climate runs have done. That would be a scenario like A2 or A1 FI. That this is roughly what's behind it.
Is that just fossil fuel energy or all sorts of?
This is all energy, including non-commercial energy in some of the models. You know, like traditional biomass, but then modern biomass, nuclear, and so on. But only the fossil one accounts for the emissions.
Did you want to say something about how you got that 3 in the CO2 emissions?
This one here?
No, in the far right.
For the far right, yeah. Well, yes, I can say a few words about it. In the scenarios that try to understand a little bit better how one might achieve more sustainable development paths, the energy demand is usually relatively low for primary energy, and much of the energy is already decarbonized, if you wish. That in those scenarios, even though fossils are today about 80% of global energy is fossil, so toward the end of the century that might decrease to 50% or 20% in some of those scenarios that pursue the idea of shifting away from the fossils. In that case, the emissions increase would be relatively low. And so you have de facto a reduction in the global emissions. But these are very heavy-handed policy scenarios. I think that needs to be said, you know. Even if you don't make explicit assumptions about Kyoto, you make assumptions about equity, about investments in technologies that are now expensive, and so on. So that explains the lower bound. And the upper bound, I think, is a little bit more intuitively clear. It's just we do what we are doing today for next 100 years, basically.
Is that sort of the burn everything? I mean, Can we really burn 33 times more CO2 in the next century than?
You mean from the point of view of carbon?
Yeah.
Oh yeah, yeah, yeah. I didn't put it in this talk actually. Have some graphs, and the most recent one that Steve's colleague Jay did. I think that intuitively, I can show it later if there is time, but I think I'm already running out of time. The resource endowment is absolutely huge. So let me just put it this way in a nutshell. About 1,000 gigatons of carbon are locked into conventional oil reserves. That's what we can extract today, gas reserves, and coal. And 1,000 gigatons is more than what we already have in the atmosphere. Now, if you go into unconventional stuff, for which we will probably develop technologies over the next decades, then that number increases at least fivefold. And if you add the completely speculative things like hydrates, then it's almost infinite, the amount of carbon we can burn. So that's not really the limitation. Limitation is technology, social acceptance, and so on.
So you're talking about like the tar sands and oil shale?
Yes,
all that kind of
yeah, all of that stuff, yeah. Deep gas, but also hydrates to an extent. I mean, what's relatively little known is, for example, Russians have drilled into hydrates in Siberia and have produced some gas. It is possible, it's just not economically attractive, but it's physically, it's doable. But very difficult, of course. So let me show you what are some of our conclusions about the scenarios now in AR4, because one of the tasks was to look what was new in the literature ever since the SRES and TAR publication, what needs to be modified, and what effect that might have on the future emission paths. So I don't know if it makes much sense to read all of this, but maybe these 3 bullets are important. The new scenarios do not show any significant change in the ranges of the emission outcomes. That means the total uncertainty of anthropogenic emissions. However, there was a significant downward revision in the population projections just in the last 5 years. So that's a big effect, and that of course will have effect on the emissions, at least on average. The reason for that is, can I save that for, I had the transparency behind it, it's easier to explain. Another thing that probably doesn't concern you much, but does concern those of us who have been doing modeling. There has been a big dispute, how do you measure economic output, whether in market exchange rates or purchasing power parity, and supposedly that would have a big effect on emissions. Our conclusion is, based on the newer literature, that probably is not going to affect the range of the emissions, but it will affect many other things in the scenarios, but not the emission outcomes. So I wanted to show you the population. I'll try to explain what happened here. So this is the state of the art of the literature, and it gives you the impression of the complexity. So the lowest population projections about 10 years ago looked something like that, 6 billion, curving to a maximum. Highest on the order of 19 billion. These were all of these concerns about population explosion. In SRES, we had 3 trajectories to cover about 90% of the range. A median, a high, and a low. High was 15 billion. Low, as you can see, was on the order of 7 billion. Now, these are the new population projections that are not all yet embedded in the emission scenarios. These are now population projections.
The blue stayed the same.
The blue is the old range, just for comparison. So you can see what the difference is, yeah? And so you can see there is a large number of projections. They're about 2 billion lower, so I've done this so you can see basically what happens. At the high end, at the median, and at the low end, we lose about 2 and more billion people in 100 years from now. So that's a significant change. The reason for that primarily, and this is very stylized, is the continuing reductions in fertility worldwide. So my demographic colleagues, whenever they do a new generation of scenarios, always revise the fertility downward.
What's been happening, if you look at past projections, from UN and various places, the real world fertility rates over the past 20 years have consistently undershot what the demographers projected. So it's been falling on average, faster than projected, and that's what results in this.
Now, one interesting thing that fascinated me when I first read about it, I didn't realize that, is that the older generation of demographic projections that was done like 10 years ago, they had this idea of convergence in there, that fertility might decline and starts from different levels, but eventually will converge toward replacement in many of the scenarios. That means in some areas, like in Europe, it would actually go up. And that was a kind of a political mandate in the UN. And I think most of the demographic groups have abandoned that. They are following the road that Steve identified, where one actually puts some more empirical numbers and projects them in the future. And that has led to significantly lower projections.
Is that just because the fertility rate's lower as countries industrialize, and so you just, as more countries industrialize, you get lower global rate?
I don't, I'm not a demographer, but I can just cite my colleagues who are demographers. I think the only thing where they really agree that does determine the fertility rates is education of women. But I guess education in general, but education in women in particular lowers the fertility. Because I think one concept that they have is desired fertility, that the desired fertility goes down.
You mentioned that the reduction of population projection does not affect much on the CO2 emission.
Not on the range, but it affects the scenarios themselves, of course.
What about land use projection?
That's a good question. I cannot answer it right now. I just don't know, but I would assume that we'll have some impacts because the agricultural production, everything else being equal, will be a little bit lower. But the trouble is that there's so many other assumptions go into it about dietary habits and so on.
So may or may not.
But I can't answer that question because I simply don't know. Once the lower projections are implemented, what the modeling teams will be doing else, what other corrections they will be doing at the same time. So, Linda?
Going back to the change from the SRES populations to these newer ones, it seems to me that you made some qualitative uncertainty statements about likelihood, and obviously a number of people have actually quantified the uncertainty around the populations. So let's say take the the SRES A2 scenario, which I think is one that went up to 15 billion.
Yes.
Would you say that now, based on whatever information you or your colleagues have, is that is definitively less likely?
Our new B2 version has to the tune of 13 or 12 billion now.
A2.
A2, I'm sorry, A2. So we have gone down from 15, A2 had 15 billion, that was the highest among the SRES populations. Our new version has more than 2 billion people less.
Oh, I see.
Okay, so we have updated that.
But still called an A.
We still call it A2. Okay. I think A2R we call it, revised.
A2, new A2.
How did it end up, the discussion that Steve Schneider and others raised about putting likelihood on different scenarios?
Well,
How much time do you have?
Yeah, exactly. It's unsettled. Let's put it that way. They are. Well, maybe a better way of explaining is the following. There are a number of scenario sets now in the literature that are based on probabilistic Monte Carlo approaches. So we have that kind of literature. The different issue that is unsettled is, that Steve was asking for, is to attach subjective likelihood to the scenarios. In the SRES, the writing team didn't do that. Some groups do it, others don't. It's unsettled. I think the reasons against it from my point of view would be that many of the drivers are related, so you would really have to look at the emission outcomes and assign likelihood just to the emission. You cannot assign likelihood to the whole scenario from my point of view.
So you could disaggregate and then assign.
Yeah, but then you lose the context that population is linked to the emissions and GDP. I think it's non-trivial issue, but as I said, there are a number of ensembles of probabilistic scenarios where you can explicitly then derive the PDFs from the population. Doing PDF on SRES scenarios is possible. We have done the frequency distributions, but the problem is that the scenarios are related. They're not independent. They're derivatives of each other. So how you deal with that, I would say, if I were to be asked to do that, I would divide SRES into 4 categories and then do likelihood on the 4 categories rather than on the individual scenarios. But I don't think there is an answer to it.
Would the categories be the families?
The families, yeah, because they have different stories behind them.
And another question, in the recent thinking, has recarbonization become more of a discussion in terms of the carbon intensity of the energy part of it.
You mean increasing?
Yeah, increasing.
Yeah. No, I wouldn't say that the carbon intensity is increasing. It's a historical trend toward lower carbon intensities. Just last 10 years has been a kind of a pause, I would say.
I'm referring to Marty Hofford and others have been talking about the number of coal plants of a traditional type that are coming online. Something like 850. So that's where I've heard conversation about.
Well, I mean, to translate that into the scenario language, we have scenarios for that. This is like an A2 scenario. This is the type of world where India and China and even US would build coal power plants because coal is cheaper today, and oil is perceived to be limited or more expensive. And then when you do stabilization with that kind of scenario, then modeling teams assume that there will be some carbon removal and storage to cut the emissions down. But I mean, that possibility is in there. I mean, we have now in the world about 4,000 gigawatts of power plants. That's 4 terawatts of power plants. And the majority will have to be replaced during the next 30 to 40 years. And so that will actually probably lock us into whether it's going to be lots of coal or lots of renewable, how the energy mix would look like, this capital replacement. And that's happening near term.
One last thing is the carbon intensity of not the carbon, but the energy intensity of the economy.
Yeah.
What's happening to that?
That's declining in general. That's declining roughly at about 1% per year. Roughly 1% per year. That's a historical trend. Now, to get to some of the stabilization scenarios, you have to double that and maybe increase it even 4 or 5 times. Detlef, just at this meeting this morning, was presenting his 3-watt scenario. That's very similar to also our, and I guess Steve and their colleagues' 3-watt world. In that scenario, the emissions have to decline at about 4% per year when the peak is achieved. So for that, you need, huge energy efficiency improvements and so. I don't remember. Let's say in 20 years from now or something like that. Okay, I'll have to skip through this because we're chatting a lot. I don't think I can cover all of the material. This just gives you an impression of and you can look later at transparencies of how the current GDP projections look like compared to the literature at the time of the stress. This is maybe more interesting for you, the spaghettis on emissions. Just as you see that we have a couple of uncertainties. The way I interpreted the TAR uncertainty temperature map, and I hope that's consistent with your views, is that about half of that uncertainty there is because of this, and the other half is because of the climate sensitivity. So this does make a difference. So these decisions over the next 10 to 20 years will make a difference. And as you can see, the range continues to be huge. One interesting thing is that there are now some new mitigation scenarios. These are just the baselines that actually dip into the negative emissions as well. And that's a strategy of growing, for example, lots of biomass and removing carbon and storing it. Now this comes, I think, more or less directly from Steve's work. I don't know if you physically developed this chart, Steve, but that might be interesting for you. These are the sulfur, the literature on sulfur emissions, how it has changed. These contours are sulfur emissions in stress scenarios, and this is the newer literature in here, and this is the old full range of the literature. You can see that sulfur emissions have gone down, and this has been also always one of the very controversial topics in IPCC. SRES already toward toward very high reduction in sulfur, but in retrospect it was not enough. It was not enough. The current emissions are significantly lower, so that's yet another big change in SRES.
So we can already predict that the next round of surface temperature change in AR5 will be behind your head just because of that.
Could be, if this is what is reflected in the new scenarios, yeah.
But some of the SRES, they're right in the middle of some of the literature range, so it's not going to be as dramatic. Because before, IS92A is not on there, but it went, way up to the top of this graph.
Yeah.
and the except for some of the SRES, the sort of B2, B1, the A1, they were nowhere near that. So that isn't, any differences will be certainly smaller.
Well, it's smaller than the difference from the change before was larger, the change in the 90s. If I remember correctly, the emission profiles for climate runs before used to simply lock sulfur to carbon ratio to be constant over the time horizon. And then this was a huge change, that actually that linkage is broken. And now I think the new literature basically says it's broken a little bit more than before. So it's a gradual change rather than a revolution. Now this is, that comes to your question, whether we have tried to link. We have tried to link. So these are the new stabilization scenarios that we have picked from the literature. Many of them multi-gas. We have divided them in the chapter into 5 categories. You can see here, this is the category that's at less than 420 ppmv. CO2 only. For CO2 equivalent, you add roughly, I would say, about 100 ppm across the range to get all of the ppms of all of the gases in CO2 equivalent. And these are the times when the emissions would peak. I think this is also quite interesting that the peaks are all usually in the first half of the century. Only for the high stabilization levels you can move to the second. This is how it looks in the models. We didn't produce that in the chapter. We picked this up from the models. This is the year when the emissions are drop below the 2000 level, and this is the percentage change in 2050 and 2100 to 2000 emissions. So it just shows how large the decline might have to be in some of the scenarios. So this is, I think, in particular, this category A is quite a new literature, and I personally think it would be interesting to know for the climate outcomes what that means.
We have a year that drops below the 2000 level for the emissions. Is that CO2 equivalent or just the CO2?
I think this is CO2 equivalent, but I'm not sure, to be honest. I would have to look it up. So in any case, I just wanted to alert you to this new category of scenarios that I think, at least from the human dimensions, is an interesting category because it's trying to implement some of those more extreme policies. This morning in the SNOWMAS meeting, there was also the discussion. It was a group that Bill Nordhaus organized about the what an extreme climate outcome in the coming decades or even during the century might mean for the socioeconomic reactions. And it's usually these kind of scenarios that have the highest capacity to respond to such big surprises. That's at least my interpretation. So here, what are some of the outcomes in TAR with respect to the stabilization and mitigation scenarios? I'll just read it. Major difference to TAR. Studies suggest that it is technically feasible to stabilize greenhouse gas emissions concentrations at levels significantly lower than the lowest level in TAR. In TAR, it was not possible to get a consensus among the lead authors, as far as I recall, of going far below 450. The literature was very sparse. But now there is quite a lot of peer-reviewed literature that is below that level. That's that category A. Most of the low emissions scenarios imply a temporal overshoot of the target. That's another significant thing, that many of the scenarios are overshoot scenarios. So concentrations go up, and then you have to reduce them more radically later. And I think that's one of the reasons why some of the modeling groups include carbon capture and storage from biomass. It's an effective way of removing carbon. I think there is a potential issue of consistency here because climate outcomes of these low stabilization scenarios are, as far as I can tell, not analyzed yet. I mean, I've seen yesterday the scenarios where one goes up to the current concentrations and keeps them flat. From the economic point of view, that's a difficult one to digest because of the inertia of the system. But I mean, it is that type of development that one needs to look at, I think, to understand what these low emissions scenarios imply. And the new multi-gas literature indicates that for a specific stabilization target, emissions might peak later in time compared to TAR. And I think this is simply an outcome that before we were looking at CO2 only. Now, as we look at all of the gases, there are more degrees of freedom when you can reduce the emissions. These are some of the other findings of the AR4, that mitigation and adaptation complement each other. I think this is a big push. That's at least my perception now, to look at the two at the same time, because we'll not be able to mitigate all of it. There will be always some residual impacts to which one would have to adapt. And so that linkage, I think, appears to be ever more important. But there are serious gaps concerning trade-offs between mitigation, adaptation, and residual impacts from the point of view of literature. So that was very difficult to do it in the chapter and continues to be controversial. Mitigation costs depend strongly on the long-term socioeconomic and technological development paths and assumptions. This is the simplest way to express it is to say it's a baseline dependency. If you're in a very high emissions world, it is more difficult to reduce the emissions than if you start with a lower baseline. It sounds trivial, but it's not trivial from the point of view of what kind of strategies would have to be in place in the future. The cost, I guess this is completely intuitive, rise relatively sharply with the stringency of the target. So those kind of less A-class scenarios that go for very low stabilization will have generally higher costs associated with them. Marginal costs increase, but they're very uncertain, and that climate policy-induced technological change leads to significant mitigation cost reductions. This is based on some of the newer literature that developed over the 90s and is now coming into the IPCC review. These are the so-called models that have induced technological change, and in this case, climate-induced technological change. And they seem to suggest that the costs could be lower for mitigation if there is a perception that climate is a big issue, and then that promotes the diffusion of new technologies. But I expect this to be very controversial. We'll see what happens after the review. And that the importance of multi-gas strategies for cost effectiveness is really essential. That significantly lowers the cost if you have the freedom of choosing which gases to reduce when and where. Now, technology is, I think, coming ever more on the far front. I think this should not be a narrow interpretation. I think there is an institutional dimension to this too, but that the technical measures are one of the major keys. I think one of the conclusions is that the improved understanding of complexity of the multiple driving forces of technological change, so that there is this new modeling approaches, I think, give a little bit more angle of understanding the dynamics of technology, that there is a wide portfolio of emissions reduction measures that are necessary to achieve stabilization cost effectively. So in most of the scenarios, a very wide portfolio of technologies is used. So I think this is a very important finding. It's not just biomass or nuclear or energy savings, it's all of those things together, plus land use changes. There is quite a lot of now discussions in IPCC, in contrast to before, in the current report, about this idea of a possible lock-in that's related to the question of hundreds of new core power plants. Once you build them, they're going to be there and might lock you in a very carbon-intensive development path. And that relationship to stabilization then is quite complex and might require peaking of the emissions before one can drop them down. So in other words, if you're off on the wrong trajectory, it's going to be more difficult to do it. And then the linkage between the short-term and the long-term issues. I just wanted to draw your attention to this number. It might be of interest to you. I was surprised that we came up, given the uncertainties, with a kind of almost a threshold number, about $20 per ton of CO2 equivalent. That's roughly $100 per ton of C. That's a threshold. If there is a carbon value that exceeds that, quite lots of mitigation occurs in most of these modeling approaches. That's one of the conclusions. Staying below that value would be very difficult to reduce the emissions a lot. It's one generic finding that I'm surprised that it came out, despite all of the uncertainties, that relatively clear. Now, I wanted to show you this. How much time do I still have?
Another 15 minutes.
Okay, good. Okay. I wanted to show you one thing that's perhaps not always well understood with respect to the emission scenarios, how much technologies there already are in the baselines that we talk about. Because, you know, when you look at the mitigation, it's clear that we have to add some of the carbon lean technologies to reduce the reductions. But the trouble is, from the modeling point of view, that we already have many of those in the baseline. So I just wanted to illustrate that to you. All modeling groups put lots of assumptions. This is an example of the 4 SRES baselines that we have developed at IASA. The fossil intensive, high economic growth A1, the balanced A1 scenario, high economic growth, the high population, low economic growth, and the median B2. And I'll just show you what we do here is do a completely hypothetical to freeze all of the parameters at the base year and let the population and GDP growth and see how much emissions we would have if this were the current system that would be providing that future affluence and future population. And you can see 150 gigatons. So of course you can take that with a grain of salt, but it gives you an illustration of how much technological progress there already is in the baselines that we are producing. So stabilization is a difficult job once you already have all of those technologies. So the baseline already includes all of the cost-effective technologies, and then in these 4 cases we go down to 550, and these are the options that one would then in addition have to invoke, and in many of them there is quite lots of carbon capture and storage. So that I think that's another challenge as one looks in the future of the stabilization from a relatively high baseline, because much of the potential in other technologies is already used. This is another way of illustrating the same. This graph is now in chapter 3. How high the reduction would be. This is this hypothetical case where everything is frozen to the base year. The cumulative in emissions in that case would be on the order of 3,000 gigatons of carbon. But if you want to go down to 550, then our cumulative emissions are about 1,000 or less than 1,000. So it's a factor of 5 reduction in cumulative emissions over the century. So that sort of indicates the importance of the technology and structural change that's embodied in these kind of scenarios. And this is the outcome that's going to be probably in the technical summary of the working group 3. It indicates some of those numbers for 4 model runs that were included in the set that we prepared for the working group 1. 4 model runs for very low stabilization level of about 2 degrees. The marginal cost of abatement, you can see, can be very high, up to $100. This is the total amount of carbon dioxide that is in the reference case. And this comes from the bottom-up sectorial analysis of how much reduction one could achieve in various sectors in each of these different scenarios. So I think the number that's really interesting is at the bottom. About in the medium term, this is to 2030. Potential reductions might be on the order of 30 to 40% in those scenarios. Looking bottom up, what kind of measures you can do in houses, what kind of measures you can do in transport sector, in industry, and so on. So that's going to be one of the integrative tables or something like that in chapter 3 that tries to rate sectorial mitigation potentials in the short run to some of the long-term stabilization trajectories. Another thing that might be of interest that I thought to show is where there might be synergies and trade-offs of climate policies with other policies. Increasing evidence, there is an increasing evidence that climate mitigation measures may create synergies, in particular with sustainable development. And I think Richard knows very well that has been always a big topic in IPCC, but there was never a decision to do a report on that special issue. But there is no doubt, and I've tried to allude to that in a scenario with relatively low emissions, is easier to achieve stabilization than in a scenario with high emissions. So there is a synergy here. Another one that's really essential, and we are working hard on that at IASA and some other groups also, is to understand better the synergies between air pollution and climate. And it works both ways. Reducing climate is usually beneficial for air pollution, but many, not all, air pollution measures would be also beneficial for climate. So there is also some symmetry breaking there, and that relationship is important. I think the new topical thing that we should look at as a scenario community a little bit more is the relationship between climates and security issues. Climate protection and security via these socioeconomic systems. And that can also probably work both ways. There is an issue of displacement of local populations. I think that's going to be high in the Working Group 3 conclusions. The benefits for biodiversity of mitigation, soil, water conservation, reduction of wasteland.
what's the displacement of local populations from?
Well, from if you wouldn't avoid the climate change, that's how I understand it. So that's a synergy of climate mitigation policies with the other socioeconomic dimensions discussed in Working Group 3 report. I think this isn't it one of the problems of IPCC? All comes at the same level of priority, even though some problem might be high and some low. But okay, so now I'm coming to the last part in the last few minutes, speculation of what might happen. So what a year ago, this is just a very anecdotal and brief account. IPCC organized this task force on new emission scenarios. I was on that task force, and we had a number of meetings and a very elaborate drafting process. There was one meeting in Washington, one at IASA in Austria, and then last March one in Sevilla to prepare everything for the IPCC plenary in Mauritius. And basically, these are some of the three categories that was felt by this task force group that would be important for the new emission scenarios, if you wish, as what are the clients for the emission scenarios, if IPCC is in climates, that all the working groups should be served, and there should be some consistency between the assessments of impacts, adaptation, vulnerability, and so on. That the assessment of emissions should be consistent with views on socioeconomic drivers and land use change and possible feedbacks from climate. And finally, that impacts, adaptation, and vulnerability are in their turn dependent on those socioeconomic drivers and land use. So I think all of these three bullets that were inherent part of that report indicate this kind of need to integrate, that scenarios could have an integrating role, the new scenarios. So that was, I think, for me at least, an important starting point. And then after much of the debate, three alternatives were identified. They are now void, so this is just only for the historical merit. There were basically, one idea was that IPCC really just focuses on the traditional assessment. It basically doesn't do anything in the scenario area. Scenario community does the scenario, IPCC assesses them. That's actually what's happening now in the AR4 and nothing else than that. But one has to say that even this option does imply some inducement, because if IPCC does something, the modeling community usually tries to anticipate and do the next round of results. Then the next one was that IPCC would facilitate establishment of some kind of mechanism for generating new scenarios. And then the new word was now introduced, catalyzing. Frankly, I don't know what the difference is. Maybe Richard does, but yeah, well, in any case. So there were different words used, but you get the idea. The idea is that IPCC is somehow involved in coordination, but it's a very soft, hands-off coordination. And the third one was a real straw man from my point of view, that IPCC develops scenarios. I think that would be more or less almost impossible, because the modeling teams have to develop scenarios. The modeling community has to do it. But in any case, there were three, and there was quite lots of consensus emerging on the B1B option.
The B2, to be fair, was what people meant by that was the stress process or something like that, right?
Well, I would say a stronger version of SRES, because in SRES didn't produce scenarios either. Modeling teams produced the scenarios, SRES packaged them.
You all met as a group, and
That's
under
correct.
IPCC auspices decided what those scenarios would
Yeah.
be.
No, I think in this case, what might have been meant is that IPCC organizes a writing team or a number of writing teams that decides how the scenarios are done.
So back to the IS-92 model.
Yeah, something like that. Maybe IS-92 model or SRES or something in between.
So how did SRES, which one of these was SRES?
Well, as Richard said, maybe it was some combination of these two, I would say.
But IS-92A, was IS-92A?
IS-92A was more like this.
IS-92A was done with a modeling framework.
One model, yeah.
There was no community participation.
And was done, I think what's important, sorry to interrupt you, it's important to note that IS-92 were done more or less during the plenary. They were done in China. I mean, the ASF modeling team prepared lots of scenarios, but they went there and IPCC actually decided what the scenario should be like in the plenary, as far as I know. I was not there, but That's the account I remember. So
And SRES, IPCC kind of formed this group of
yeah,
people.
IPCC made terms of reference. I don't know how they came about. Maybe you do, but they came explicit terms of.
Emerged fully formed from Bob Watson's.
Okay, okay. So IPCC produced terms of reference and then appointed the writing team, and then the writing team solicited modeling teams. There was an open process where people were asked to contribute, and then the writing team also solicited the expertise and designed the storylines, and they were given to the modeling teams to quantify. Steve? Oh, sorry, Linda. Yeah, sorry.
But I have a very trivial question, so I'll go fast. B1A, B1B, B2, were there any A options, or did you establish a just an ersatz numbering system?
Yeah, no, that's a good point. You have to remember, this is an evolutionary process. It started with an equal attribution of letters, I think. It was A, B, and C. And then as options got eliminated and bifurcated from one meeting to the other, this is what ended up.
You have to understand a lot of this was driven by politics, not by the desire of the modelers or what they would have recommended.
Well, I remember explicitly, I think Jay chaired one of the sessions where some of these variants appeared because we said, you know, B1 makes no sense the way it's designed, let's go for a B version of it, and then the letters stay. But in any case, this was not adopted by IPCC. So what was adopted is the following, the way I understand it. I was not in Mauritius, I don't know if any of you were there. I read the chairman's resolution, and I think concerning the role of scenarios in AR5, it says something of this sort, that the panel recognized that the development of scenarios would be undertaken by the scientific community, at least, or it implies not by IPCC. The IPCC may catalyze such a work, so that's the word, such a work as to promote its readiness in time for the AR5, and that's the timing that I talked about before. So it has to happen quickly. Then IPCC would eventually prepare a technical paper, it was not clear to me by when, to summarize the relevant material from the AR4 and to identify a small number of benchmark emission scenarios. And I've tried to do that based on our writing team work. So something of that sort, a dozen, maybe 24 benchmark scenarios from the literature for potential use by the climate modeling teams, groups of the IPCC. And then there should be a steering committee to organize a meeting involving relative communities and I guess to lead to the technical paper. Do you want to add something to that, Richard?
Well, only that I thought when they used a small number, they were talking about a much smaller number like N of 3.
Well, maybe 3 baselines, but then when you multiply it with stabilization cases.
Well, the point was to try to cover the range of the scenarios that's in the literature, with not make too many demands on the climate model community by saying you could take a low, medium, and high, which would include the stabilization case, and then you would, in a parallel process, the socioeconomic modeling teams would do a lot of the underlying socioeconomics that really don't affect, except for the short-lived species, what you do in the climate model.
I mean,
the idea is to decouple a little bit the socioeconomic scenarios from the ones that go to the climate.
And the rationale for trying to do that is twofold. One, to reduce the demands on the climate modeling community, and second, to try to enable the climate modeling and the underlying socioeconomic modeling to go on in parallel to reduce the time required for all of this to unfold.
Steve?
Well, I think we've got there's different requirements. If you're talking about a climate model output from a GCM, N is no greater than 3. How many modeling groups did more than 3? Almost none, if any. And you can't even distinguish them if you did. So, but for example, we've talked a lot about land use. Have some that's still at a much earlier stage of modeling. There's going to be some very different land use.
Sure. Yeah.
So if you had your larger benchmark set, then land use model components may want to do a larger set of experiments to see identify what the consequences of that is. That's right. So
But are you saying those as experiments or as scenarios that then get
actually
projected into the impacts?
They may need. Impacts. where impacts depend on land use, maybe you do want a larger number of scenarios to cover that uncertainty. I mean, I don't know.
Well, I think that would be a really useful input for this group to try to offer some suggestions about it.
And actually, we need this meeting of impacts modelers to try to figure out, well, how many land use scenarios would you need? What would be relevant?
Yeah.
And I don't know the answer to that question, but it might be greater than 3. Well, Linda says it's 7, so there we go.
You want a number, you got a number.
But in any case, I think this is why one needs this, both the technical paper and the steering group to try to figure out how many benchmarks, for what purposes, and so on.
So the other question, just I was talking with Jerry earlier, I mean, the time scale for an IPCC technical paper is not this fall, by any stretch of the imagination. But so what's the time scale that, and of course I guess the AR5 model time scale is not quite this fall either. So is that congruent? Jerry, do you think that the IPCC could come up with this in time that you would the community be wanting to be doing AR5 runs, or is maybe that too long if they're not? What would be?
Well, it's probably too long. But it depends on when. Like, is this technical paper actually going to happen? I mean, is there a group that's organizing this?
No, it's going to be all organized. It's all in the future.
Yeah.
But nobody. I mean, is somebody actually doing it?
Well, I understand, IPCC is charged with it. I've seen some terms of the reference. I think Richard is perhaps more familiar. What I remember is there should be some people on it who were in the task force. There should be some people from the Working Group 1, Working Group 2, some other experts like involving, International Energy Agency, OECD. That's what I remember on the language.
And it may be there needs to be some catalysis on the other end. For example, if the outcome of this meeting is, well, we need to know our 3 GCM scenarios by X date. That's probably the needed benchmark to get something started, either IPCC or not.
Well, or at least if not by a date, by a number of years ahead of when product can be delivered.
I kind of have a big picture question I don't understand. Writing these notes, and I just started reading, and I know I don't understand. The idea of a common emission scenario. In the next generation models, we're going to be predicting in each model the concentration of CO2.
Yeah.
So we're not going to have a common CO2 concentrations in principle from model to model to model.
Yeah.
So what's it mean for the various groups to share?
Yeah. Well,
share this.
No, I think that's a good
sharing
question.
Emission scenarios doesn't mean you're sharing concentrations.
Well, but we already have that with the new stabilization cases, because the actual concentrations will vary from model to model as well, because these are all usually integrated models. To achieve stabilization, you already have to have some rudimentary climate in your model to be able to work backwards to the emission profiles. It's all solved simultaneously. Now, since in the climate models, part of that problem will be also endogenous to the model, we have two approaches that have huge overlaps.
Well, they may not be stabilization once they get into a climate model.
I don't know what the answer is. I mean, the only thing I would think about is some kind of categorization within intervals.
Well, and that's something, actually, I'll talk a little bit about later in the meeting, but it's actually possible that that's not a, Ron, that's actually not that's a question that can be answered, because, the integrated assessment models should, certainly do now, and should continue to have the capability to mimic the global behavior of carbon cycle models in GCMs. We can already do that with various complex carbon cycle models. So we can actually make sure it is a stabilization scenario if the appropriate benchmarking is done beforehand.
But it's conceivable to me that one AOGCM might, as an emission scenario, might be stabilization, where in another one it won't.
Right.
Yeah, exactly.
Yeah.
Why would,
Yeah.
I mean, if you're interested in stabilisation, why would you not prescribe the CO2 scenario and
Well,
diagnose the
because
fluxes?
we'll be using whatever this
Well,
group comes
that's
up
actually
with
a
as
good
input.
point. But that's a good point, though. If you
Yeah.
want to do that, you can do it that way.
You
It's
decouple
prescribe
it
the
then.
concentrations.
So although you're running in a coupled system,
We can always do the idealized.
no, but it's not idealised. I mean, it's basically diagnosing the fluxes.
So it's idealized in the sense of we're just
and
going to
therefore backing
give
out
it.
the emissions.
We don't have an emission scenario that's connected to it.
You
We're
don't
just-
need to.
you would diagnose the emissions consistent with the CO2
So that's a good point. It's a different, for a mitigation, for a stabilization scenario, it could be a different mode of operation.
It's much easier to do stabilisation.
Is that
Because then
really,
you back out, I mean, basically the client modelling comes first, right, and you back out from each of your coupled models what the scenarios consistent with stabilisation at a given level are. And then you work out from socioeconomics whether that's feasible or not.
Yeah,
For that
it's kind
matter,
of
the
inverse
integrated-
calculation.
Yeah, it's, you do it the other way around. The whole thing turns
And
on
actually,
its
that's not, the integrated assessment models can already do that.
Yeah.
I mean, we can already vary carbon cycle parameters and back out the implications, and I'll show that later on, the implications of the carbon cycle uncertainty for the emissions.
Right.
I mean, that's something we will continue to be able to do. So that's.
But
Well,
in
that's already-
in the next generation models, you could do it that way, and you also then decouple the carbon problem from the climate change.
Well, I would certainly also
Which I think is a good
minimize
thing, actually.
would minimize the amount of time necessary for the round.
Yeah,
Would make the whole process much faster.
but you would be focusing specifically on
Yeah.
specific stabilisation emission scenarios.
But I think,
Stabilisation concentration scenarios.
but this discussion implies that benchmarking might mean something else than might have originally been meant here. So that needs to be discussed.
You could do it. I mean, you could do it even right now with like B1.
Yeah.
You could have an implied mitigation. You could extract from that. And we already have those running.
And then really all you need to do is you need the other gases, but that's something the models can provide, sort of generically for a broad stabilization level. There's not an incredibly broad variation in the other gases once you get the stabilization scenarios. So, you just put those in.
another
And
dumb
then you say,
question.
well, is that feasible?
Yeah.
When you're saying stabilization, are we talking about radiative forcing, or are we talking about concentrations of some gases?
Well, that's a good question. We have in chapter 3 decided to go to watts per square meter for looking at the categories, but we also report CO2 and CO2 equivalent concentrations. So we report all 3 categories.
Effectively, it's not that big of an issue because CO2 is so dominant by the end of the century in a mitigation case that stabilizing total radiative forcing is effectively equivalent to stabilizing CO2, and any differences are going to be lost in the noise in a GCM. So I think
Is that
for
really true if you have a big indirect effect for aerosols?
Yep, the aerosols just aren't there in a mitigation case because you're not emitting sulfate anymore.
Yeah, but they're going out of the atmosphere, so the radiative forcing
From lack of aerosols.
for lack of aerosols is
But
big.
by the end of, so there's a transition effect where those effects are important, but by the time you get the stabilization at the end of the century, it's pretty much a pure greenhouse gas signal.
Problem gets so much easier with stabilisation. It goes back to the old equilibrium climate sensitivity stuff. Just not easy, but
David?
I've
Two
done it.
questions. One, for AR4, was there any thought about having emissions of other potential aerosol precursors, like soot or black carbon or things affecting organic aerosols?
Yeah, well, in AR4, the scenarios that are assessed in AR4 are those that are in the literature. And we tried to sample just the 6 greenhouse gases and 4 other substances like VOCs, methane, SOx and NOx. And we have not looked at whether the modeling teams are reporting carbon black and soot and so on. We have not compared that. Some teams do report it.
There's only a few that do. I mean,
Ours does.
does it, we do it.
But we have not included that in the assessment. That's all I'm saying. When we assessed the new scenarios, that was not part of our metric because relatively few scenarios in the literature do that.
And I know you were talking about this with Linda before, but what exactly is the relationship between what CCSP has done for their 2.1 in their stabilization scenarios that they produced?
And maybe Linda should answer that. I mean, I've not reviewed everything. I've just reviewed a part of that report.
CCSP synthesis reports 2.1.
The emission scenario.
The emission scenario for stabilization.
Right.
Yes.
What about them?
How do they relate to AR4?
They don't because it's not published, so it's post AR4.
They're not in AR4, if that's your question.
Some of the same models.
Some of the same models, some of the scenarios will be similar, I presume, but not very same.
Yeah. So they're different scenarios.
I just talked to yesterday to John Houghton, and he thinks that there might be some approval to be able to quote the scenarios so they can be put in the assessment. But the deadline for working group 3 was something like 20th of July, so I don't know whether that's still possible or
There's
not.
some, I mean, there's this connection between, I can't remember, 3.1 and 3.2, between the emission scenarios, and the next product is climate model runs with those scenarios, and I see the prospectus just went online for comment. And so there's this coordination issue of, you know, the scenarios aren't finalized yet, but can they be used for GCMs? And of course, practically speaking, changes probably won't have any effect. So that's being worked out right now.
But presumably there'll be some changes after the review process, right? But they will not be so big that it'll make any difference.
Right, especially on for GCM.
Now, I just had the last bullet I wanted to alert you to, and this one that IPCC has also approached the Earth System Science Partnership to help with the process of identifying new scenarios. So I think this is something that maybe it's good for this community to know that there might be this partnership between IPCC and ESSP. So this is the end.
There's the detection and attribution folks keep making the case that they don't want standardized concentrations. What they want is a set of standardized forcings, or at least to know what the forcings are coming out of the models. And all this stuff complicates that to another degree, to the point where, you know, you're going from concentrations to forcings, which vary by the implementation of various models and other things, the nonlinears in the model, and then to climate change effects. And so trying to relate those back becomes increasingly difficult, because you could have models doing processes differently, which they all do. Is there any way to standardize these things for the forcing? Because we still don't even have the standardized forcings in the AR4.
These are all future. What yours
Right, and my
is
point
for
is
the
that if we
20th
start
century.
thinking about this now, from the scenarios to getting, maybe translate the scenarios into the standard set of forcings for the models instead of the standard set of concentrations, it might be a useful alternative to consider. Because there's a community out there that thinks that is a better idea.
Well, I think it gets rid of some of the ambiguities, whether you're talking about CO2 or CO2 or all gases.
Well, as you said,
It's a single number.
your stabilization targets are in watts per meter squared.
Well, that's how we reported them, but we report concentrations along the lines in the chapter, because I guess because of this discussion, it's not clear. Some communities think more intuitively in terms of ppm, other in terms of watts per square meter.
The follow-up on Dave's point is that a weakness in the IPCC has been that the historical forcings aren't being addressed by any group. And the modeling groups do whatever they want, which then creates problems for the detection attribution people,
Okay. Yeah.
which is another set of
Yeah,
problems.
I see.
But I mean, if you're reporting in watts per meter squared, that had to have been run through some model from concentrations
Oh yeah,
to radiant transfer, right?
And these are integrated models. They have simplified carbon cycling models built into them or decoupled to them.
So what do you think the prospect, this idea of a benchmark, just a couple of benchmark kind of scenarios that would be somehow representative of, so I was trying to follow all the different scenario possibilities, and it looks like you've got, like A, B, C, and D are A, B, C, D, and E. There's 5 new kind of classes
For the stabilization
for
cases.
stabilization.
Yeah.
And each one of those has a baseline.
Has a
and each one
baseline,
has a stable.
Well, what we have tried to do in that set, that was perhaps too large for the working group 1 purposes, we tried to capture 2 effects. One is different stabilization levels, and the other one is going to the same stabilization level from different baselines. Both problems from our side are very interesting, because if you're stabilizing from 2 different trajectories, that's a fundamentally different dynamics, even though the stabilization level is the same. And so we tried to do a combination, a balanced combination, that we covered those both dimensions. So that in the area of 4.5 watts stabilization, we had a couple of baselines. For the 3 watt stabilization, we had only 1 baseline, if I remember correctly. And then for the high one, we had 2 baselines as well. And the problem of that is that it multiplies the number of scenarios. But I think what Steve and Richard had implied, I think when it comes to the climate outcomes, many of the scenarios will be similar and maybe can be grouped in the same category. But at least we know what the drivers were. So when you do impacts afterwards or adaptation, one would have this additional information in addition to the climate information.
And it would still be consistent.
Yeah, it would be broadly consistent, yeah.
And what was actually, I don't know if this was formally done, but what was by the impacts folks or not, but what was informally done at least was a mapping of, well, here's the scenarios that the GCMs ran, and here's what analogs of the underlying scenarios that are essentially equivalent for impacts purposes that you could use, if you don't have a GCM run or you don't want to do a SenGen scaling or something like that. So that can be done as part of that.
That's a kind of inverse thing that Peter was talking about, right? Where you say you've got some run, and that implies certain things could have happened, and then you can string together a scenario based on. Start with the EOGCM result and then work backwards to some scenario.
Well, in a sense, you have this wide set of emission scenarios from the integrated assessment modelers, and there's whole sets of scenarios that could be mapped to one GCM run, equivalently within the noise, and then. But there are issues that one has to examine there in terms of, say, regional sulfate and so on, because some of that can differ quite dramatically, even though the global result doesn't. But
as far as I remember, Tijika, that Richard co-chairs, did that a few years ago based on TAR. There was a mapping of GCM runs to SRES scenarios and the TAR stabilizations. It was a kind of a matrix that I think Morita-san did, Lake Morita did that. Huh?
Rob did it.
Okay, yeah. So there is a precedence. One can look at that table and think how we could adopt it to these new ideas. It gave a two-dimensional mapping of scenarios and climate runs, and indicated which of the scenarios of the SRES and the TAR family belong to which category of the climate runs.
That reminds me of a question about some of the changes that have already occurred. So you indicated the A2 population is lowered by what it was
2-3 billion.
2-3 billion. Now, if one were to then take that new and improved A2, and because the population is lower, that would certainly probably change the land use cover change, and some other things, which would end up creating a different climate, would it not?
If you would force me to answer that question, my best guess would be to say that this is a second order of magnitude issue. I think that probably will not change the climate run that's associated with that scenario that much, compared to going to a B2 world or B1 world. So I think these modifications, even though they're important from the consistency and modeling point of view, I think they're marginal with respect to their relation to climate.
Well, that would be good to know.
When you say that, do you mean in the magnitude and rate, or do you also mean the pattern of change?
That's even more difficult to guess.
For the impacts people, it's the pattern of change, and that's an important question to address here is, can you use a pattern scaling technique?
Well, the first order effect pattern is determined by the GCM, not the input scenario. And then second order effects would largely be changes in regional sulfate. And those would be restricted, to the extent they exist, would be restricted to the near term. And there are pattern scaling techniques that take into account sulfate as well. I mean, SenGen does that. So, for example, these things can be done.
I still think, coming back to this earlier discussion about trying to map these scenarios onto a high, medium, and low emission scenario at the end, I still come back to a related question to you. You're still going to have for this next generation, or maybe it's AR4 or AR5, you're going to need a gridded land use that's consistent with that. Right. So you're not just going to average the land use maps of the underlying scenarios, I don't think.
Yeah, but that already exists for many of these scenarios, for modified versions or original versions.
You can average the emissions that come out of them. You can't average the land use map that produced them.
Well, we're not talking about averaging emissions.
No.
So, I mean, that was actually goes back to what I said before, is that if you had, one of the G's, say if one of the three, GCN, whatever they were, reference scenarios or whatever the terminology was, was the YASA scenario.
Benchmark.
And then benchmark scenario, thank you. And it would have a certain land use associated with what they produced. Then if you looked at our scenario, it would have a different land use.
Yeah.
So maybe it had similar overall emissions so that the climate change, but it had different land use, then, well, one could investigate what the sensitivity to what that was. So that might be another part of the sensitivity for the community to explore.
Yeah.
But isn't it?
But that's something that would be, you could even do, you could certainly do, in a sense, offline. I mean, not in the fully coupled mode to do that sort of sensitivity as well. And then you could see how important it was.
Yeah, I don't know. I mean, there's the whole mesoscale modeling community thinks that the existence of the Amazon rainforest is at some threshold of land cover change that could tip it to become, desertified versus a rainforest. They don't know what that threshold value is yet, and so that you can't do that study offline because it's a couple of climate land surface problems.
Well, thanks, Nikki, and we're going to be returning to these scenarios.